So far in this chapter, we've encountered two important big ideas. They are the concepts of work, the line integral of the force over some path. If the force is constant, you can write this as the magnitude of the force times the magnitude of the displacement times cosine of the angle between those two things. So that's one big thing we have talked about. And the other is the work kinetic energy theorem. That tells us if you add up the work done by all forces acting on an object as it moves along some path, then that tells you the change in this thing we call the kinetic energy, where K is half mv squared. It's energy associated with mass in motion. The third important concept or idea in this chapter is that of potential energy. What I want to do here is introduce to you the notion of potential energy. I'll show you the result first, and then I'll show you where it comes from, and then we'll look at some examples and problems. It turns out that for some forces, not for all forces, but for some forces, I'm leaving a big gap here because I'm going to come back and give this thing a name in a bit, but for some forces, when you evaluate this integral up here, when you take a force, whatever the force might be, and you evaluate f dot ds from some initial location along some path to some final location, what you end up with is the difference between two scalar functions. And it's a scalar function evaluated at the initial position minus the scalar function evaluated at some final position. And no matter what path you take with that force, you always end up with the same thing, the same scalar function evaluated at initial minus the same one evaluated at the final, which is to say it's minus the change in that scalar function. So for that force that this applies to, we call this the potential energy function. So this is the potential energy. Now let me point out again that the work done depends on the potential energy function evaluated at the two endpoints, but it's independent of the path. It doesn't matter what the path was. Now, what kind of forces are these? Well, first let's give them a name. We call them conservative forces. So I'm going to erase the word some here and put in conservative forces. For conservative forces, this applies. How do you know if a force is conservative or not? The best test is to check to see if the curl of the force field equals 0. If it does, the force is conservative, and this will apply. If it doesn't, the force is not conservative, and this does not apply. If you haven't encountered the curl operation yet in your calculus, don't worry, you can always just do this. If you have a force and you want to know if it's conservative or not, integrate the force over some path and see if what you get is the difference between two scalar functions, one at the initial minus the same one at the final. If that's what you get, the force is conservative. And by the way, this implies that for a conservative force, the work done on a round trip, if I take some closed path, if I evaluate f dot ds on some closed path, I'm going to get 0. Because I'll have some scalar function at some location minus the same scalar function at the same location because I took around a trip, so I'm going to get 0. The work done by a conservative force on a round trip over a closed path always equals 0. That's another test you can make to see if the force you're dealing with is conservative. If the object moves around a closed path, does that force do 0 work on the object? If it does, the force is conservative. Okay, let me show you why this notion of potential energy is a useful thing. Hopefully we can see straight away that what it does for us is it gives us an easy way to evaluate the work done by some force. Instead of evaluating this integral every time, or evaluating force times delta r times cosine of phi, all I need to do is take minus the difference in some scalar function. That's an easy way to evaluate the work done by this conservative force. Another way to see this is to substitute this result into our work kinetic energy theorem. So let me write that up here, and we'll see how that goes. Suppose we had an object that was moving around some path and there were several forces acting on it. There could be gravity and friction and tension and any number of other things. I want to separate now the work done by all forces into two bits. I want to separate it into the work done by conservative forces, the ones that this applies to, plus the work done by so-called other forces. And by other forces, I mean forces other than those that we're going to write a potential energy function for. So all becomes conservative forces plus other forces, and that's going to equal delta K. Now for each conservative force, we can identify a potential energy function, and WC for each one becomes minus delta U. So we have minus delta U plus work other equals delta K. Solve this for work other. Delta K plus delta U. All right. I like to rewrite this equation one more time, and then we'll define some terms and talk about it. These deltas are in every case final minus initial, final kinetic minus initial kinetic, final potential energy minus initial potential energy. Take those initials with a minus sign in front of them and move them to the left-hand side so that we end up with this. Work done by other forces, forces we don't have a potential energy function for, plus the initial kinetic energy, plus the initial potential energy, equals the final kinetic energy plus the final potential energy. This is a statement of what we call energy conservation. It tells me that if I know how much energy I start with, there are two kinds of energy now. There's kinetic energy, which is energy associated with mass in motion. So tell me how much kinetic energy there is, and then tell me how much potential energy there is. As we've written it here, potential energy is a kind of energy that's associated with the location of an object in a region where there's a conservative force. So tell me the sum of those two kinds of energy at the beginning of some motion, and tell me how much work happens along the way. And then I know how much energy we end up with in the end. This is very much a bookkeeping exercise now. It's like if you're checking your bank statement at the end of the month. If you know how much money you start with, maybe this is your checking account and this is your savings account, how much money you start with, how much money gets deposited along the way by doing work, that will tell you how much money you end up with. The energy could change pots. You could change from kinetic to potential and do some work and end up with a whole bunch of potential energy over here, but the sum is always going to be the same. The sum of the initial energy plus the deposits due to work is going to equal the sum of the final. You can move them around in between these two pots, kinetic and potential, but the sum is going to be the same as what you started with plus how much you deposited by doing work along the way. This is a very insightful way to think about work. What is work? It is a way of having a force act on an object and deposit energy into the system as the object's moving. You start out with some amount of energy. There's two kinds. You can deposit or take out energy. Take out if you do negative work, and that tells you how much energy you end up with in the end. These two kinds of energy, kinetic and potential, we lump together and we call them mechanical energy. There are in nature all kinds of energy that we talk about. These two combined are what we call mechanical energy. So same thing here. So now we can say our conservation of energy equation is telling us if you know how much mechanical energy you start with, and you know how much gets deposited or taken out through work, then you know how much mechanical energy you end up with. Okay, so that's the notion of potential energy. If you have a conservative force, the potential energy gives you a convenient way to evaluate the work done by that force. There are, as it turns out, two kinds of conservative forces that we'll encounter in this class. In the next talk, we'll look at both of those, we'll obtain their potential energy functions, and then move into some examples.